Hello, ladies and gentlemen. Mr. Dorfler here with another daily dose of Dorfler, and it's one of our last ones we're going to have for the semester. So, yay on that. Another yay that we're going to have today is what we're talking about, and that is using molarities, which we talked about yesterday, in stoichiometric calculations, going all the way back to chapter 3. We spent so much time on that because we enjoyed it, and we get to do one more round of it today. Don't worry, okay? You are given a flow chart, and here is that flow chart. It looks very similar to the flow charts we've had before, okay? As you see here, right in the heart of this flow chart is converting between moles of substance A and moles of substance B. Again, the substance A is what we know. What information do we have on a particular substance? Substance B is what we're trying to determine, solve for, okay? Really, one of the only difference between this flow chart and other flow charts is we're just going to be incorporating molarity. So once we get to substance B, our unknown, and how many moles we have, we can use the volume in liters of substance B to get the molarity, or go the other direction and use the molarity to help determine how much volume of substance B we would need in neutralization reactions. It's really what we're looking at in using this flow chart for, is neutralization reactions, okay? So oftentimes we use stoichiometry and molarities in a process called titration, okay? We don't typically do titration in here. It's usually an AP Chem practice because it is a very analytical technique. I'm going to move my guy down here. And it's a technique that you can use to help calculate the concentration of a solute in a solution. As we'll see when we do some of our practice exercises, this is a very industrial process to where industries will determine what a known or what a concentration of a substance is and compare it to what it should be, okay? Because they have to have parameters of certain solutions, and if they are outside either too strong or too weak from those parameters, then they have to make adjustments to the whatever process they're doing. So basically, what happens is you start off with a flask, an Erlenmeyer flask, okay? And you add 20 mils of acid solution to this flask, okay? You add a few drops of what's called an acid-base indicator, and then inside what's called a burette. I used to have them hanging up in my classroom, but we've moved them to the supply room because they are kind of expensive lab equipment and wanted to get them out of the way. But they're they can range, but typically anywhere between 30 to 36 inches in length. And it's got about 50 milliliters that is marked on there. And right at the very bottom, if you can see where my arrow is here, right here is a little turn device that you turn. Every time you turn, it allows very small amounts of the solution, in this case the base in this burette, into the solution of acid. And you continue to do that until you start to see a faint pink color. Now, this is probably a little too pink for this purpose, but obviously they wanted you to see it. That acid-base indicator will cause the color of the solution to change to a pink color when you've reached what's called an equivalence point. That's where basically you have neutralization between the acid and base occur. And so after you've reached that equivalence point, you then determine how much in terms of volume did you use of the base inside this burette. That base has a known concentration, and so we can use that in conjunction with our flow charts to help determine what the concentration of that acid was. So it's a pretty neat technique, but one of the most important things that you need to have in this process, and it goes back to chapter 3 as well, you have to have a balanced chemical equation. If you do not have a balanced chemical equation, you're not going to be able to solve for this because you need to use the mole ratios between the substances in the reaction in order to help go from moles of A to moles of B, okay? So let's take let's take a look at our first sample problem here. We are asked to figure out how many grams of calcium hydroxide are needed to neutralize 25 milliliters of 0.100 molar nitric acid. Okay? Well, the first thing is, you want to pay attention to what you have and what you need to solve for. We need to figure out how many grams of calcium hydroxide are needed to fully neutralize this volume of this concentration of nitric acid. One thing you also want to make sure that you pay attention to are units, okay? So we need to first determine how many moles of our substance A, which is nitric acid, because that's what we know, how many moles do we have that present? And we're going to use the molarity equation and rearrange it to solve for moles. But remember that molarity must have the volume in liters of solution in liters, okay? So we have to convert 25 milliliters to liters. Once we have determined how many moles we have, we need to go from moles of nitric acid to moles of calcium hydroxide. But at the very beginning, what you need to do, and again, you can do this at any point up until now, but I highly encourage you to do it at the very beginning, and that is do your balanced chemical equation, okay? So let's first, the book goes ahead and solves for the moles first. So they use the molarity equation, rearrange it to solve for moles. So you have your volume times your concentration, your molarity of your nitric acid. And again, they've converted the volume of 25 milliliters to liters. And they come to find out they have 2.5 times 10 to the negative third moles of HNO3. So in order to go from moles of A to moles of B, and B is again our calcium hydroxide, we have to have a balanced chemical equation. Well, since this is a neutralization reaction, we know that one of the products is going to be liquid H2O, and the other one is going to be a salt. And so basically you're going to do-si-do. That hydrogen is going to go with the OH, calcium is going to go with the nitrate. And so you're going to get H2O liquid plus calcium nitrate. Once you've determined your products, go ahead and balance it. You see they place a coefficient of 2 in front of the nitric acid and the water. And so there is a 2 to 1 mole ratio between nitric acid and calcium hydroxide. Okay, so 2 to 1. So we place our amount of moles that we calculated for nitric acid. We use the mole ratio. We need calcium hydroxide in our final answer. And so they have 1 mole calcium hydroxide over 2 moles of nitric acid. Again, that's coming from the coefficients. And they went ahead and tagged on to this this calculation, the conversion of how to go from moles of B to grams of B. They use the molar mass of calcium hydroxide. You can make this a completely separate calculation if you want to. So after you have solved the 2.5 times 10 to the negative third moles and use the mole ratio to convert to moles of calcium hydroxide, that determines how many moles of calcium hydroxide you used. Then you could do a separate calculation if you wanted to using molar mass of calcium hydroxide to help determine how many grams are needed. And so you find out you need 0.0926 grams of calcium hydroxide. Okay, so really we're using very similar steps to what we've already spent a great amount of time on in chapter 3, except we're just adding in molarity, which we did quite a bit of practice with yesterday. Okay, let's look at a practice question. Okay, it's a 2-parter. Okay, they're going to be separate questions in this case. So let's look at A first. How many grams of sodium hydroxide are needed to neutralize 20 milliliters of 0.150 molar sulfuric acid solution? Okay, we'll come back to B here in just a second. Okay, so I can never get my camera right. Dim the lights. All right, so what I like to do first, before I do any type of calculation, is I like to get my balanced chemical equation out of the way. So I know I've got H2SO4 aqueous plus, I'm going to give a little room just in case I need to add a coefficient in front of the sodium hydroxide. And again, they're going to yield, since it's a neutralization reaction, they're going to yield H2O as a liquid plus sodium sulfate Okay. So again, water and a salt. So again, to balance this, you can take time if you need to. You can pause the video now if you need to. You're going to put a 2 in front of the sodium hydroxide and a 2 in front of the H2O. Okay, so there's your balanced chemical equation. I'm going to keep that at the very top. First thing we need to do, we need to figure out how many moles of sulfuric acid we have. Again, that's our substance A. So moles of H2SO4. I'm going to, again, I'm using the molarity equation and rearrange it to where I'm going to have my liters of H2SO4 multiplied by our molarity of H2SO4. And again, we were told that we had 20 milliliters of sulfuric acid. We need to divide that by 1,000 to get liters. And so we're going to get 0.020 liters multiplied by 0.150 moles over liter. Again, that's what molarity is, moles over liter. Liters cancel, and we're left with 0.003 moles of H2SO4. So that's how many moles of H2SO4 we have now. Next step is we need to determine how many, how many moles, and then actually ultimately our ending answer needs to be in grams. So I'm going to take the step that the book takes, and I'm going to incorporate into this final calculation how we solve for grams. Okay, so we're solving for grams of sodium. Oops, a little sloppy there. Sodium hydroxide. Okay, so we're just going to use the moles we have of sulfuric acid, okay, because that's what we know, 0.003 moles H2SO4. Then I'm going to multiply it by the mole ratio. We find that we have a coefficient of 2 in front of sodium hydroxide and no coefficient in front of the sulfuric acid. So it's a 2-to-1 sodium hydroxide to sulfuric acid. So 2 moles of NaOH goes on top, and 1 mole of H2SO4 goes on bottom. And like I mentioned, excuse me, I'm going to do the final step and use the molar mass of sodium hydroxide to help determine how many grams of sodium hydroxide are needed. And so, again, determining the molar mass, you have to look at the formula, look at the periodic table, sum up all the elements in their individual masses, and we will get 40.0 grams NaOH per mole. So if you go ahead and place this into your calculator, you should get 0.240 grams of sodium hydroxide needed. Okay, if you need to go back and see that again, you have the power. Next, I'm going to go to question B. Okay, question B says, eventually, how many liters of 0.5 molar hydrochloric acid are needed to react completely with 0.100 mole of lead to nitrate, forming the precipitate of lead to chloride, which is a solid? Okay, well, we're told what is formed. Okay, so first thing is I'm going to do a balanced chemical equation. So again, this is going to be kind of a do-si-do reaction. So we've got HCl plus lead 2 nitrate, PbNO3 2. And these are both aqueous. Sorry, you can't read that. That's going to yield, as we're told, the precipitate PbCl2 as well as HNO3, which just happens to be a nitric acid. So we're not dealing with a neutralization reaction here. We were never told that because we don't have two We don't have a strong acid or strong base or anything like that reacting together. Okay, so it's not a neutralization reaction, but we can still solve it no matter what. So again, we need to balance coefficient of 2 in front of the HCl and a coefficient of 2 in front of the HNO3. So now we need to figure out what we have. Okay, now according to this problem, it says we have 0.1 mole of lead 2 nitrate. Okay, that's what we know. We're trying to figure out how many liters of hydrochloric acid we need with this particular concentration. So the hydrochloric acid, since we're solving for something dealing with that, that's our substance B. Our substance A is going to be lead 2 nitrate. So we know that we have 0.100 mole of lead 2 nitrate. We're going to then go from moles of substance A to moles of substance B using the balanced chemical equation. And we're going to find that we have our substance A, or B, I'm sorry, is hydrochloric acid, and it has coefficient 2. So that's 2 moles HCl per 1 mole lead 2 nitrate. Okay, we go ahead and solve for that, and we get 0.2 moles of HCl. Now, next thing, we are trying to figure out how many liters are needed. And so if I go back here, I am now at this flow chart where I'm at moles of substance B. And I need to figure out the volume of the solution containing substance B. So in order to go from here to here, I have to use the molarity of solution containing B. Well, we are told what the molarity is. Okay? First off, since we're solving for liters, again, we're using the molarity calculation, except we're solving for liters. So we're going to have liters is equal to moles over molarity. Okay, so that means liters is equal to 0.2 moles of HCl, which we got right here, divided by 0.500 molarity. Yeah, I'm just going to cross that out. Why did I write that? Stop writing the moles for molarity. There we go. Just out of habit anymore. We've been doing moles so many times. So go ahead and solve for this, and you're going to say 0.400 liters. So that is how much, in terms of volume, will be needed of the 0.5 molar hydrochloric acid to react completely with 0.1 mole lead 2 nitrate. Okay? So again, most important thing is balanced chemical equation, and then using that flow chart and identifying who's who. We got a couple more problems to go through. Okay? A couple more problems, and that's it. Back to this, back to this. All right. So, as I said in the beginning of this video, that this is this whole process of titration is a very technical, analytical, necessary process and test to help determine concentrations of certain solutions. And this sample exercise right here is a great example as to what I'm talking about. Okay. One commercial method used to peel potatoes is to soak them in sodium hydroxide solution for a short time. Then remove them and spray off the peel. The sodium hydroxide concentration is normally 3 to 6 molar. And the solution must be analyzed periodically, because if it is too weak, it's not going to peel the potatoes. If it's too strong, that can have some serious consequences for the potatoes and possibly the consumers of those potatoes. In one such analysis, 45.7 milliliters of 0.5 molar H2SO4 is required to neutralize 20 milliliters of sodium hydroxide. Now, I want to pause, because in the example that we saw here, we had acid being placed into the flask and base placed into here. It can go either way. You can have an acid in the burette and a base in here, or as we see here, a base in the flask and or an acid in the flask and a base in the burette. Okay, so it doesn't matter. Doesn't matter. Anyway, let's get back to this. And we saw that it required 45.7 milliliters of 0.5 molar H2SO4 to neutralize 20 milliliters of sodium hydroxide solution. What is the concentration of the sodium hydroxide solutions? Well, again, they kind of go one step before you get to the balanced chemical equation, but I always encourage you to do the balanced chemical equation first. Again, it's a neutralization reaction. We're told that. We also know that because we are reacting strong acid with a strong base. So we're going to get a water and a salt. Okay. What we do know is we know how much volume and what concentration of the sulfuric acid was used. And so again, we can use the molarity equation, solve for moles. So you're going to have moles of sulfuric acid is equal to the volume in liters multiplied by the concentration of sulfuric acid. Again, they went ahead and put the conversion in here, 45.7 milliliters divided by 1,000. That gives you your liters. And then multiply it by the, excuse me, by the concentration of 0.5 molar, and you get 2.28 times 10 to the negative second moles of H2SO4. And again, we are using that flow chart, that T-shaped flow chart. Okay, so now we go from moles of A, which is sulfuric acid, to moles of B, which is sodium hydroxide, using the mole ratio. We then place the number of moles of sulfuric acid, use the mole ratio from the balanced chemical equation, and we find that we have 4.56 times 10 to the negative second moles of sodium hydroxide. The last step we need to do is we need to determine the concentration of said sodium hydroxide. And instead of going the way we went before, where in the last problem we worked on, we had to find the volume, we're going to go this way, over to the left side. We need to find the molarity. And so we're going to use the volume that we were told of in the very beginning, that 20 milliliters. Okay? So, again, we're going to take our moles that we just calculated for sodium hydroxide, and we're going to divide it by the volume in liters, which is what they are doing here. Okay, I don't like how they show. I'd rather do the conversion outside of the calculation, but it's up to you. Okay, but this is what it would look like. So converting 20 milliliters to liters in this fashion, and we find that we have a concentration of 2.28 molar sodium hydroxide, which, according to the problem, it says it needs to normally be between 3 and 6. Well, we found out that it is below our lowest point. So adjustments to that process and that solution would have to be made in order to meet this operating criteria. See, just a small little analytical test, and we know that the process needs to be altered a little bit. Last question, folks, here. What is the molarity of a sodium hydroxide solution if 48.0 milliliter neutralizes 35.0 milliliters of 0.144 sulfuric acid? Okay, so again, I'm starting off with a balanced chemical equation. Sodium hydroxide plus sulfuric acid is going to form water in the liquid form plus a salt, Na2SO4. Okay, to balance this, I need to place a 2 in front of the sodium hydroxide and a 2 in front of the H2O. So again, I need to figure out how many moles of sulfuric acid I have, because that's what we know most of. Okay, we are being asked to figure out values in terms of sodium hydroxide. So, moles of H2SO4. This is our substance A. Again, I'm going to take my 35 mils of sodium hydroxide divided by 1,000, and we're going to get 0.035 liters, and multiply it by the concentration of sulfuric acid of 0.1. Oop, that is not a 1. 0.144 moles per liter. Allows the liters to cancel out. And you should get a total number of moles of 0.00504 moles of H2SO4. All right, so now we have moles of substance A, and we can go to our next step and determine moles of substance B, which is going to be our sodium hydroxide. We're going to take what we just calculated, 0.0054 moles of H2SO4, and multiply it by, or then use the mole ratio of the balanced chemical equation of 2 moles of NaOH over 1 mole of H2SO4. Calculate that out. You get 0.01008 moles of NaOH. So now that we have our moles of sodium hydroxide, we then need to determine our molarity of sodium hydroxide. And so that's going to be moles over liters, which we're going to be using our moles of 0.01008 moles. And we were told that in the problem, we used 48.0 milliliters to neutralize it. So again, 48 divided by 1,000, we're going to get 0.048. And so 0.048 liters. So our molarity should be 0.21 molar. Again, everything was derived and solved for. And if you need to pause the video to go back over this or rewind it, you can. But everything was derived from this flow chart, okay? Got to have your balanced chemical equation first and foremost, in my opinion. Then you determine who is substance A. It's going to be the one that you know the most information about. Your substance B is going to be what you know least, as well as what you are trying to find out or solve for that particular substance, okay? And so then you have your choice, either determine the volume or the molarity, or sometimes even the grams. Well, you can just use the molar mass for that. Anyway, that is going to put a wrap on Chapter 4 notes, ladies and gentlemen. I'm not going to do the last couple of slides here because I'm not going to bother you with that. But we are at the end of the chapter. All righty. Anyway, if you have any questions regarding this, please let me know. Well, till next time. Bye-bye.